Today's demonstration is of a Phantom 3 drone equipped with our digital dog nose sensors. The components are a data acquisition system, which is this black box here, a laptop computer that has the right software in it, the drone, which is a Phantom 3, and located on the drone are two of our sensors.
So to make these sensors, you start with a substrate. We use it's Yttria stabilized zirconia, YSZ. It's very specific to our sensors because it localizes the heat. This allows the sensors to heat more efficiently and operate at lower power. And so you take that substrate and you do a process called photolithography, where you basically adhere a polymer to the surface of the substrate and open up windows, which allows us to deposit the sensor material onto the substrate itself in our very specific orientations.
The actual sensors weigh almost nothing, okay? So ideally suited for a drone, because drone payloads are, at a premium. In other words, the drones, they can't take big payloads unless you have a very large drone. And so a lot of the trends is smaller drones with very small payloads. And some drones have payloads on the order of grams. And so you can't have a large sensor to do that. The sensors are mounted on the drone. There's two of them. One is a reference and one is an active sensor, which is essentially a microheater with a catalyst covering the microheater. And we look at the heat effect associated with the decomposition of the target molecule. In this case, the drone will fly through a cloud of molecules at very low concentrations, and we will be able to pick that up. That is, the sensors can pick that up at very low levels. Typically, our sensors can detect explosives at the part per trillion level. That's a really tiny concentration of explosive in the air. Our sensors are vapor sensors. We only detect things in the vapor. So the drone is going up to about 5 feet. Peter will spray the target molecules, and the sensor will detect the molecules.
So on the computer screen are two signals, basically. One is the catalyst-coated sensor that detects the analyte of interest, whether it's an explosive or a biological material. And then the other is the reference, which basically just mitigates, if there's a large wind gust or if there's any changes in flow rate, that sensor will be subtracted from the signal of the catalyst-coated sensor in order to get a very clean response.
Our signal is really a measure of the heat effect associated with the decomposition of the target molecule. And so consequently, because explosive molecules give off so much energy, we're able to track that to very low levels. Because the drone is flying, there's all kinds of airflow that you have to take into account, temperature effects, wind, for example. And so the reference is needed so we can subtract out the signal that you get from the catalyst sensor, and that's why we have a reference sensors.
And so on the computer screen is the real-time response of the sensors. So when they're flown in over an analyte source, in real time, you're detecting that analyte. You're watching the response of the sensor in the presence of the analyte, and then also when you've moved away from the analyte, you see that the response returns back to its original baseline.
So the only signal, ideally, we're getting is the signal from the interaction of the chemical compound with our sensor. For the purpose of today's demonstration, you'll see a couple of wires interfaced to the laptop. We are working on a wireless version, which is really not researched because the components and the systems are out there already. And so that is not a particularly difficult problem. It's an engineering problem that we're working on. The real difficult problem is our sensor being able to detect this cloud of threat, whatever it is, and get back to some user, okay, that can identify that threat. That's the whole point.
So today we're seeing that when the drone flies over the analyte source, let's say in the box example, as soon as it crosses over the path of the box where there's vapors, exuding from the package, the sensor response just goes through the roof, and it's detecting the analyte of interest that's inside the box. Same goes with the spray acetone testing. So when the vapor is sprayed into the air and the drone flies through it, as soon as it passes through the vapor, you get a response, and there you go. And that's all shown on the computer screen. The response of the sensor is quantitative and qualitative. So just from those responses, you can identify the type of explosive you're looking at and its concentration, which is all important for detection.
It's very akin to what a dog does. When a dog picks up a scent, the dog is really picking out molecules in the air and responding to those molecules in the air. And that's exactly what our device does. It's been trained, if you will, just like a digital dog knows. It's been trained via the catalyst that we down select and that has been tuned for that particular molecule.
A drone is just such an obvious next step forward for this technology. If you can fly into an area and identify your explosive threat and make your plan going forward from there, it's just so much easier than putting any sort of life in harm's way, whether it's a dog or a human being.
Wouldn't it be safer, instead of sending a human being in to determine, is that an explosive, is that dangerous, is that a threat? You have a UAV, you have some kind of autonomous vehicle that can go in with our sensors mounted on it, essentially sniff out the box, okay, tell whether it's a threat or not, and then fly out with no real risk to human life. And that's really the nice part about a drone, is there's no real risk.
Sensors of this type that are low power, portable, can be put on drones or a robot that can be driven into a venue. It can really just protect anybody out in the public.
Dogs' attention span is about an hour and a half, maybe 2 hours. They need a break. They need to regroup, essentially, and they respond to treats. You give them some kind of treat, and so they have limited attention span. They're very good at what they do, and very reliable. But we need to be looking out there at these threats 24/7, and that's what dogs can't do. So you need lots of dogs to do that. Basically, wherever you see trained dogs that have been trained to detect drugs or trained to detect explosives or bombs or whatever, we can train our sensors to do very similar things.
So today is the culmination of 15 years of sensor research. So 15 years from Dr. Gregory, 5 years from myself. Basically, what we've done and what we are doing is taking these sensors that we've been developing and minimizing power and minimizing weight and actually adding them to an application where they're useful. And so here we are putting them on the drone themselves so that way they can be experimentally tested for different applications. So whether you're in an airport and you're flying around with a smaller drone, or you're in a battle zone where there's larger explosive threats and they can be flown in on maybe a UAV-sized drone. This is kind of the beginning of that process of actually taking something that we've been developing the sensor itself for so long and actually putting it in an application where it can be useful.
And so the payback is that we want the Department of Homeland Security to have yet one more tool in their toolbox against the fight against terrorism. I guess that's the simplest way to put it.